All right, Prop 27 says, if a straight line falling on two straight lines make the alternate angles equal to one another, the straight lines will be parallel to one another. So if you are, at this point, really sick of triangles, good news. This doesn't have anything to do with triangles. At least the sort of the claim doesn't have anything to do with triangles. Bad news. We're going to prove the claim by using triangles. Right, so what is this even saying? It's saying, imagine that we have some line, EF, that is falling along two other lines, AB, in such a way that it makes the alternate angles equal to one another. So there are some choices for what we consider to be alternate angles. We could call this angle right here, this is an alternate angle to this angle right here. What else are the alternate angles? Is this angle right here, AEF, is alternate to EFD. So that's what is meant by alternate angles. It is a little bit confusing. It's not alternate angles in the way that, like, whichever previous proposition it was that was saying that alternate angles are equal to each other. So, like, in that proposition, it was saying these would be alternate angles. Here, it's not saying that. It's kind of saying, like, alternate angles on the opposite sides of this transversal of EF. So, okay. So the claim is that we want to prove that the lines are parallel to one another, and this is kind of the first time in the propositions that parallel is really being brought up at all. So just as a reminder, the definition of parallel, let's see, it's definition 23, and it just says two lines are parallel if they never touch each other. So what we really need to prove here is that AB does not ever touch CD, given that the alternate angles are equal. So which are the alternate angles that we claim to be equal? We claim, yeah, AEF is going to be equal to EFD. So proof, we'll say let angle AEF, close my window really quick, sounds like somebody's doing some cleaning. Angle AEF is equal to angle EFD. So that's the hypothesis. We're saying that AEF is equal to EFD. What we want to prove is that AB is parallel to CD. And that's kind of a tough claim. That's a really strong claim, saying, yeah, AB never touches CD. How do you prove that? Well, one hopefully intuitive way of proving that is by contradiction. Assume that AB does touch CD, that we have this equality of the alternate angles, but AB still touches CD, and we'll see if we can reduce it to an absurdity. All right, well, I'll say, again, just to make it obvious that this is a contradiction. Toward a contradiction, assume AB meets CD at G, where, without loss of generality, who's John? I don't know. AB meets CD at G, where, without loss of generality, because we need to choose the side that G is falling on, because AB could meet CD over here on the right, or it could meet on the left. Without loss of generality, we're going to say, let's assume it meets on the right. So where, how should I say it? Where without loss of generality, G lies in the direction, I believe is how Euclid says it, in the direction of B and D. So we're going to kind of assume that there's some point over here, G. So I'll draw these lines in because it looks a little bit weird, and this is always the tough thing about doing proofs by contradiction for geometry proofs, is that, you know, geometrically, like, oftentimes we can make these diagrams, and the diagrams kind of make it sort of obvious. Like, this is I mean, this is true. This proposition is true. So it's not possible to really draw a diagram that accurately shows the proof by contradiction. You have to assume that there is no angle here, that this AG is a straight line and CG is also a straight line. That's why I kind of made it dotted, just so it's like, it can be a little bit weird. The weird part comes when we're going to consider this right-hand piece a triangle, and it doesn't at all look like a triangle to us, but you have to assume, because we're living in the world of contradiction right now, that this forms a triangle. Right, so, yep. So, okay. Then, how should I say this? Angle AEF, which we have something to say about. Angle AEF is an exterior angle to this triangle that we just formed, which I'll call EFG. Right? So imagine this being a triangle, and then we're able to extend this side down, which means that AEF is an exterior angle to our triangle. Well, what does Euclid say? He says in the triangle, I guess he called it GEF, whatever, same thing. The exterior angle AEF is equal to the interior and opposite angle EFG. And he says, but this is impossible. So then triangle AEF, I'm just trying to figure out how I can write it a little bit. Well, I mean, that's pretty much the contradiction. We've reached the contradiction. I'm just trying to figure out how to write this a little bit more concisely. So angle AEF is an exterior angle to EFG. But by proposition 16, it would follow that angle AEF must be greater than angle EFG. So I'm going to say but twice in here again. But angle EFG is the same as angle EFD. So this is a contradiction. I feel like I've stated this in kind of a strange way. Right, so AEF is an exterior angle to EFG. Yep. By proposition 16, I guess I could have removed that but, and I could have just said by proposition 16, it follows that angle AEF is greater than angle EFG, but angle EFG is equal to angle EFD. So we kind of have this strange, this contradiction where we're saying angle AEF must be greater than angle EFD, but we also know from the outset we're given that they're actually equal. So it's a contradiction. So where was the assumption that we made? Was assuming that AB meets CD. So AB does not meet CD. And really, I guess, even though I said here without loss of generality, and that should just be the end of it, to really kind of shore it up, we can say AB does not meet CD in the direction of BD. Direction of B, comma D, because that's not actually a line, BD. Similarly, it can be shown AB does not meet CD in the direction of, in the other way, of A comma C. So, well, if AB never meets CD, I guess I could say that. So AB never meets CD. Hence, as we might write it today, AB is parallel to CD, which is what we wanted to prove. QED, therefore, etc.